I'll start recording now. Can you guys see my screen? Oh shit, no you guys can't. Can you guys see my screen? Yeah? Alright, cool. Hold on. Let me move this up for a second so Alrighty, so welcome to Fluids. Alright, whether this is your second year or first time with me. Alright, it's a pretty hard course no matter what. Alright, just a bit of a heads up for you guys. So what I've done here is I've laid out how I'm gonna run this crash course. So I'm gonna go through fluid properties. So these are just your topics of for this course. We'll do fluid properties, hydrostatics, continuity, energy, and then these are the main four I'm going to go through today. However, there are some other topics which I'll just briefly touch on. Alright. So fluid properties, we're pretty much just talking about fluids, like the property of fluids, right? It's in the name. Mass, weight, density, as well as viscosity. It's a bit of a weird one. Anyone know what viscosity actually is? Yes, that's a pretty good way of putting it. It's like how well it, I guess, I forgot. It's the resistance to flow. Yeah, it's how flowy it is, essentially. Alright, hydrostatics, this one requires a bit of physics. Alright, so we're looking at pressure, how pressure is measured, as well as forces on submerged bodies. So pretty much if you drop something into the ocean, what are the forces acting on that object? Right? We're going to learn how to calculate that stuff. Continuity. So this is looking at. It's a pretty small topic, but it's pretty important, right? Pretty much as fluid enters a pipe or like a certain object, how does it interact after it enters, and then what happens after as well, right? And then energy, we're looking at like some equations, head loss, which you guys probably have no idea what head loss is. I'll try my best to explain it. Okay, any questions? No? Alright, good. So other topics that you guys will see, pipe flow, dimensional analysis, physical models, boundary layer, and drag force. So pipe flow is probably the biggest topic. It's pretty much just how does fluid interact within a pipe. Right? Sounds pretty easy, it's a bit hard. Right? Dimensional analysis is like the most mind-numbing one. It's just math. Right? It's not like, this is pure theory of math, right? But it's not too hard. A physical model, I guess, builds from dimensional analysis. Boundary layers and drag force, they're pretty chill. They're pretty small topics. Okay. Alright, cool. So that's pretty much a rundown of the whole course. I guess we'll jump straight into fluid properties. So a fluid can be one of two things. It can be liquid or it can be a gas. Alright, so liquid, it has no fixed shape. However, it does have a fixed volume. So this bottle over here, you guys see how the fluid, it's got no fixed shape. Right, you can like, I guess, move around in the bottle freely. However, it does have a fixed volume. Right? Hello. So it does have a fixed volume, which means, so within it, like the amount of volume that it has won't change. Alright? Gas just has no fixed shape, no fixed volume. Alright, it's not too important. I'm just giving you guys some background knowledge. Alright, a few values that you guys are going to have to know. Density and unit weight. Density is pretty easy, mass over volume. So it's a mass per unit volume. I'm sure you guys have seen density before. So what's an example of something that's very dense? Honey? Honey it's not dense, it's viscous. Yeah, I was thinking about honey as well, but it's not that. It's actually not dense. It's viscous. Anyways, doesn't matter. I'm sure you guys have seen density before. I'm not going to go through it too much detail. The unit for it is given by kilograms per meter cubed. Right? Mass is kilograms divided by volume, which is meter cubed. Okay. Now, unit weight. This is something new. So this is the weight per unit volume. So this is pretty much just multiplied by gravity. It's just literally just your density times your gravity. There's also a derivation here, but all you guys are going to need to know is that unit weight is equal to rho g. Yeah, so we call this letter up here rho. There are some important values you're going to have to know. So for example, water. Density of water is given by 1,000 kilograms per meter cubed, or 1 gram per milliliter. Another way to put it in unit weight, 9,000, because G is just equal to 9.81, you can just multiply these values by 9.81 and you get these values. Nick, any questions? Make sense? Good. Do you guys have any questions so far? No? Sounds good. Alright, relative density or specific gravity. So we usually just call it specific gravity. Alright. In fluids we denote it as SG. Later on when you do soils we denote it as GS. But what relative density is it's the density of a certain fluid relative to the density of water. Alright? So for example, if you've got like some sort of mystery fluid in the tube, right? If you want to find the relative density of it, you compare it to the density of water. And it's got no units, it's dimensionless, right? Because it's just a ratio, right? And there's two formulas I could use. They're both equivalent, right? The reason being, if you have the unit weight of a fluid divided by unit weight of water, this is just equal to the density of fluid times gravity divided by the density of water times gravity. And gravity just cancel out, so you just get that. Make sense? Yeah, pretty chill. Yeah. It's just a ratio. Nothing really much to it. Specific volume is really weird. It's just 1 divided by density. We don't really care about it. We don't really use it too much either. So I'm just going to skip over it. Any questions? No? Alrighty. Viscosity. So, as I just mentioned, it's the resistance to flow. So, you guys can imagine in a container, or like when you apply a shear stress to a certain fluid, it's going to start moving. Pretty much just means when you apply a force from the right, it's going to start moving. You guys can imagine waves, right? Waves. Some sort of force this way, it's going to move. That's pretty much the easy way to, I guess, visualize it. Alright. Shear stress has a formula, tau. So this is given by tau. Which is equal to F on A. So when we apply this force, right, it's going to move. The fluid's going to move, which means it's going to have some sort of velocity given by U. Okay? This velocity varies, right? It changes depending on what scenario we have. So there's something called a velocity distribution, which I'll cover in just a sec. But before that, let's go through this formula really quick. So tau is equal to F on A, where F is your applied force, A is the shear area. So the best way to explain shear area I think I had something down here. Here it is. The area that the moving object is in contact with the fluid. Right? So you've got an object. This is your object. Let's say it's moving like this. This is your fluid. Right? This bottom part over here is in contact with the fluid. So what we'll have to do is we'll have to take that shear area, which is just that circle. Right? It's a bit weird, but imagine if there's a plate over here that the top of the fluid is touching, right? That part is just going to be the shear area. It's just going to be in contact, right? Law of viscosity is just a formula that you guys don't have to use. However, so this is a constant. This du on dy part is the thing that changes, right? This is given by our velocity distribution, which I'll quickly cover right now. So there's a few different scenarios in this course, right? Specifically, so you have scenario 1, 2, 3, and 4. So first scenario is when you have one moving plate, one fixed plate. So I guess you can imagine this as this bottom plate is like still, this top plate is moving. Because this top plate is moving, imagine in between these two plates there's like some sort of fluid. Yeah? So when it's both of them not moving, the fluid is static. When this top plate's moving, what happens to the fluid? Does it just stay static or does it move as well? It moves as well, yeah? So that fluid is going to start moving and it's going to stick, because of viscosity, it's going to stick to that top plate. And in this case, scenario 1 is if you have a linear distribution. It just means that that plate that's moving moves in uniform velocity. Yeah. So our velocity distribution is given by this. Any questions about the distribution right now? Why it looks like this? So there's two things we're going to have to understand. All right. Why there's some sort of velocity up here and why there's no velocity down here. As I just said, the fluid is going to stick to the object, right? That's just a property of fluids, right? Because it's going to stick to this top plate, it's going to move at the same velocity as that plate. So the fluid at this point up here is going to be moving at u, yeah? The velocity down here, because it's not moving, that bottom plate isn't moving, the fluid is just going to stay still at that point. Right, and there's distribution as we go, as we move up, yeah, the velocity, exactly. All right. Yeah, it is. So this is my shear stress distribution. It will stay the same. Mainly because the force that's being applied doesn't change, and the shear area, which is up here, the shear area doesn't change either. Yeah. So these two values are constant, therefore my shear stress is going to be constant. So a lot of people last year, they were a bit confused by what du on dy actually means. So I guess if you have a good understanding of math, shouldn't be too big of a problem, but this is a differential, right? When you do calculus in math, it's a differential, which means it's a rate of change, yeah? So this is pretty much denoting how much u changes as y changes, essentially. So pretty much we're saying, as u is being increased, how does our u change, right? So we know it's a linear distribution. Because it's a linear distribution, we're just given by, we can just give it as u divided by y. Okay? Honestly, if you don't understand the theory behind it, it doesn't matter, just use the formula. That's what I like to say. Like if you don't know what it means, just use it. Okay, second scenario is we have one moving plate again, one fixed plate. So again, top plate moving, bottom plate not moving, vice versa. However, we have a non-linear distribution, which means that the plate gets faster over time, right? This velocity distribution is now a function of y, so u is a function of y. Right. And we don't usually do this in the course, but what you'd have to do is you'd have to find u in terms of y, and then you'd have to differentiate it. You don't really do any integral. Oh, you might do a bit of integration, but you don't really do any differentiation. And we try to avoid calculus in these courses, right? As an engineer, we don't really use calculus that much. We all approximate all that bullshit, right? These are some other scenarios. So I'm not going to explain what's going on in this scenario. I'm just going to explain the shear area part, okay? Because let's say we have a plate. We have 3 plates, okay? One at the top, one at the bottom, fixed. So they don't move, but one going in between as well, okay? That's the scenario. So these two are fixed, and this one is moving. So we actually have 2 velocity distributions. We have one above on this top plate, this top part of the plate, and at the bottom part of this plate, okay? Because the fluid is in contact on both sides of the plate, our shear area is going to be doubled, okay? As I said earlier, it's the area that the moving object is in contact with the fluid. So this moving object is in contact with the fluid at both the top and the bottom part. These parts we don't really care about, it's negligible. Have these top parts we can't ignore. The top and bottom parts. So we have to multiply our shear area by 2. Similarly, for a cylinder, let's say we've got 2 cylinders, one smaller cylinder, one bigger cylinder, right? So for example, if this is the bigger cylinder, this is a small cylinder, we're dropping it in, okay? And there's going to be some sort of fluid within this bigger cylinder. What's going to happen is that as this falls, the fluid's going to, like, I guess, coat the entire area. So what's our shear area now? It's going to be then this, I guess, surface area. Yeah, exactly. It's the surface area of this object. Yeah? No. So, actually, similar reason to why we don't count this. There's no shear that acts on it. So, you can see that as it drops like this, the fluid is like going upwards. So it's actually, there's going to be some sort of stress that gets induced. Exactly. Shear can be left and right as well, but in this case, because our motion is going this way, right, there's really no shear that gets induced up here. So there might be like some sort of force pushing it down, but I'm not sure how better way to explain it. It's like, so what really is shear? It's like when the fluid or an object, I guess, like rips like that, right? Even if this thing was hollow down here and here, there would still be shear because it, I guess, cuts the fluid, right? But it doesn't happen because of these two top parts. Yeah. Yeah. I'm trying to think if there's a better way to say it. But yeah, I guess mainly because shear isn't induced up here or down here. Yeah. Okay. So any questions about fluid properties? No? So that's pretty much all of the very first topic. Done. So this is something you cover in like week 1 / a bit of week 2. They go in the lecture. They go through it into like a little bit more detail. I'm just here to let you guys know what you need to know. Right? This is why we do these crash courses. We're not going to go through it in detail. This is a brief overview of what you guys might expect over the term. Second topic, hydrostatics. So, what is hydrostatics? I gave a brief rundown on it at the beginning, but imagine you into a pool of water, you chuck in a ball or you chuck in an object, right? As it sinks, there's going to be some sort of forces acting on that object due to the water or the fluid. Hydrostatics is pretty much just a study of that, right? The forces in water or in a fluid, right? So one thing that's really, really important, pressure and depth, right? How does depth affect pressure, essentially? So this might not be as obvious, but it might be obvious actually, I don't know. But as you go deeper, the pressure acting on the object is going to increase or decrease. Increase, exactly. A good example that I like to give is, if you guys remember the Titan, I forgot what it's, Ocean Gate submarine. It was like a few years ago, like it imploded on itself. It's because it kept going, it went too deep, and then the forces got like too large, and then it just exploded inside the water. So that's a pretty good way to, I guess, visualize. As you go deeper, your pressure acting on the object is going to increase. Yeah, does that make sense? So what we have is some formulas. So a very general formula is, let's say you have a pool of water. Oh, by the way, this triangle symbol, it just denotes the top of the top of the water. Sorry, this means top of the water. So that's where the water, I guess, starts, and then you go deeper. So let's say you have a object here at some sort of depth h. Yeah, and let's say this is water. The pressure acting on this object is given by h times the unit weight of that fluid, which is water. That's a very basic formula. All right, that's if we're taking the pressure from the top of the surface water level. However, we can also find the pressure given the pressure at a different point. So if we're trying to find the pressure at point 2, and we know the pressure at point 1, right? We're just gonna know, all we need to do is, we know that this depth is given by h, which is y2 minus y1. Yeah. So the depth at P2, or the pressure at P2, is given by P1 plus that difference in height times the unit weight of the fluid. So if you want to find the pressure, it's always unit weight times depth slash height. So unit weight times height. That's how we, I guess, define pressure, or a pressure change. Alright. There's a bit of a proof here as well, if you're interested, but you're not going to get assessed on it at all. Yeah, it's also in soils. Yeah. So in soils, you'll see like layers of soil, and then you might get like water table here, and you might even see like they might ask you the pressure at this point, or like the stress at that point, right? It's given by like this times height. So I'm going to yeah, it's pretty much exactly the same. The principle is you go deeper, your stress or pressure is going to increase. Alright. There's actually a few ways we actually measure pressure when it comes to fluids. There's simple way, where simple just means there's a pipe end and there's an atmospheric end. Pipe end just means you have a pipe, right, and you have a tube going into that, and the other end of the tube connects to the atmosphere, or it just connects to open air. So that's what we mean by simple measurement of pressure. You have one pipe end, one atmospheric end. There are two devices for this, a piezometer and also a manometer, a simple manometer. Right. So over here we have the pipe end. So this is looking at the cross section of the pipe. So this is my pipe. I'm cutting it here and I'm taking a look at this way. That's the cross section. Okay. So we've got that pipe end and then the atmospheric end up here. So it connects to the atmosphere. One thing to note, the relative pressure at the atmospheric end is always going to be 0. So yeah, the pressure, I guess, of anything connected to the air, atmosphere, is going to be 0. Same thing here, so you have a pipe end, and then it does some weird shapes, and then it becomes atmospheric end. So PATM is equal to 0 always. Any questions? We also have something called a differential manometer. This is when we have two pipe ends. So we've got two pipes like this connected to each other. Okay? Within this pipe, we might have different fluids, right? So over here, this is on my iPad. Over here, we have fluid 1. In between, we have fluid 2. And then over here, we have fluid 3. Okay? The main reason for this is, as we said earlier, is to measure our pressure. These are devices to measure pressure. So what we might wonder is, what's the pressure at B? And we might know what the pressure at A already is. So here it is. This is the formula for finding the pressure at B given A. However, this will always change, right? This is just unique to this scenario. Your task is to pretty much just figure out this formula when they give you like a certain manometer. right? So you might get like a weird arrangement. You might get something like this. So let's say fluid 1 comes here, then you have another fluid here, another fluid, another one, another one. So you might get 1, 2, 3, 4, 5, 6, 7 different fluids. Right? In this case, your formula is going to change. And I'll actually show you guys how to figure out this kind of formula. One second. We actually might end a bit early, which is good. Okay, so there's a few things you're gonna have to remember. So, yeah, here it is. So this is how you pretty much figure out this kind of formula. You start from one point. So let's say I want to find the pressure at B. I'll start from point A. Okay? And what I'm going to do is, if you guys remember earlier, I said that when there's a difference in height, there's going to be a change in pressure. Yeah? You guys remember that? Yeah? When we introduce another fluid as well, there's also going to be a difference in pressure. So this fluid is going to cause a change in pressure. This fluid is going to cause a change in pressure. This fluid is going to cause a change in pressure. So when you get from point A to point B, there's 1, 2, 3 different changes in pressures, right? And this and the changes in pressure is denoted by these parts here. So I start from point A. I have a change in pressure 1, 2, 3. Add them together, and you get your pressure at B. Does that make sense? Yeah? So, this is, I guess, the rules of how I do it. Whenever you go up, so you start from a point. Let's say I'm starting at point A and I'm ending at this point here. So the start of the fluid versus the end of the fluid, right? Because that change in height is positive, what do you guys think my change in pressure is going to be? Positive or negative? So my change in height is positive. Yeah, the pressure is going to be negative. Because essentially, you're going up. And as we said earlier, the deeper you go, your pressure increases. Vice versa, the shallower you go, it's going to decrease your pressure. So when you go up, your pressure is going to decrease. When you go down, your pressure is going to increase. So this is the formula I like to use. PB, so pressure at point B, is the pressure at point A plus or minus the unit weight of the fluid times your change in height. Okay? And you're going to keep adding on terms. So you might have a different one here. You might have a different one here. You keep adding these changes in pressures based off how many fluids you have. Okay? So for example, over here, we have fluid number 1 with a unit weight of gamma 1. The change in, what's up? The change in height is given by ZA, and it's a positive change in height. What does that mean for my pressure? Negative or positive? Yeah, but in this case, it's going up, right? So it's going to be a negative. So what I've done here is gamma 1 times ZA, and I've just put a minus at the front. That makes sense? Same thing with this fluid over here. Fluid number 2, the black one, is gamma 2. Because it's Y is the change in height and it's positive, so it's going up, right? It's going to be a negative, the black one. So it's minus gamma 2 times Y. This black fluid over here. So, and this last one over here, fluid number 3, gamma 3, we start from a higher height and we end at a lower one, right? So we start up here, end down here. ZB is our change in height. It's going to be a positive change in pressure. Make sense? Then when you add these all together and you reach your end point, this will equal to your pressure at point B. Questions? Now, in that case, I get you guys to do a question here. Can you guys see that? So, what you guys need to do is determine this height h down here. Determine this height h. Given that PB minus PA is equal to 98 kilopascals, I've given you the unit weight of water and the unit weight of mercury. So this is mercury over here, this is water, and we've also got red oil. Because they've given us the SG of red oil. Okay? So from here, you're gonna need to find the unit weight of the oil. That's up to you guys to figure it out. 10 minutes, 5-10 minutes for that. And yeah, give it a go. Let's start going through this. So, first things first, find the unit weight of the oil. So the way you do that, you know that SG is to unit weight of fluid, unit weight of water. This is given to us. So, times unit weight of water, which you get to be 8096. 8096. Right. And then we're going to start from point A. I'm going to make my manometer.
SG also density of the density of water. So
Yeah. So if you want to go from density, if you want to go to density, 8096 divided by 9. Density of the fluid? Oh, density of the water. Oh, so you're trying to find density of the fluid?
Density of water. Isn't that SG?
Yeah, it is. But the reason I found this one is because when we do our calculation for pressure, we use this. We don't use density. You can use density, because if you find the density, you're going to have to multiply by G anyways, which is this. So, if you take a look here,
When I found it, all I did was I put SG as one of the SGs, right? And then I times it by 1,000. I didn't include the gravity.
yeah, so you don't need to account for gravity because we're looking at the unit weight, not density. Yeah. So what you've done is you've just done this. Yeah. However, what we need to use, well, you can use this, right? Because we know that this is equal to density of that times G. So if you found this first and then multiply by G in here, you could do that. It's a bit longer. Yeah. And also, density of water, we actually don't know. Oh no, density of water we do know. Sorry, it's always 1,000. Yep, that's right. Sorry. But yeah, you got when you do your manometer equation, you're gonna have to use
What do you want?
the equation, the manometer,
Okay.
this part over here. Because your pressure, it's not density times height, it's unit weight times height.
Right.
Yeah.
And that's density times gravity.
Yeah, exactly. Yeah. So the other way you could say is density times gravity times height.
Yeah. Oh yeah.
Is that what you've done?
No, I forgot about the gravity part.
Okay, that's good. But it makes sense, huh? Okay, good. So you start at point A, and water ends up here. So you have a change of height of h. So the change in pressure over here is just going to be minus unit weight of water times height. Make sense? Then if we look at the oil, the height difference is 18 centimeters, and we know that it's going to be unit weight of oil times 0.18. I just converted it to meters. Now, this change, oh, by the way, this should be a negative. This one is the change in height. Well, first of all, positive or negative pressure change. Yeah, this one here. Positive. Because our height. Yeah, exactly. The pressure increases, but the height decreases. Alright. So we have the unit weight of mercury times our change in height, which is 0.18, plus h plus 0.35. Make sense? Yeah. Okay, so we combine these all together. What I've done is I've taken PA to the other side because they've already given us PA minus PB minus PA. Yeah? So I know what this value is. It's just 98,000 pascals. And after a bit of rearranging, for H, you get 23.4 centimeters. Yeah? I got to double check this, but can't be asked right now. Alright, I'll go through a bit more before we take a quick break. Actually, yeah, I'll give you guys a break now for 10 minutes. Then we can get started with forces on a submerged body. This is week 2/week 3. Yeah. Like this one?
Yeah.
Yeah, this is week 2/3. I think. I don't know if they changed it, but it should be. Let me check.
They don't even give you like the answers to the final being good and
No. Yeah.
stuff. Some have it.
I don't think so. You can. I think my drive might have it. Let me check. So past finals, past papers. I think for some of them we do. Yeah. So we've got this link. It takes you to the solutions. Yep, here it is. Yeah, it takes you to the solutions. So these are. Oh, where'd it go? It's still loading. Yeah, here it is.
Oh yeah.
So yeah, it'll be in my drive, which I'll put up at the end. But yeah, yeah, I'll give you guys a 10-minute break before we continue. With this, so this is week 2. Actually, this is week 2, and then week 3 will continue after. Alright. Let me pause the recording.
Our friend who did like his entire assignment using Google. He like one shot it.
Yeah, that's why I dropped comps up. They don't need us anymore.
Can I take ENGG2400 and 1300 in the same film?
I think 1300 is a prereq for 2
Yeah. So
Yeah.
can I take it in the same film?
You could.
But you, if you want to drop 2400 to 1300, you can't get it.
You can't take 2400, yeah.
Wait, 1300, isn't that?
It is a prereq, but you're allowed to do prereqs together. So you're allowed to do 1300 and 2400 together.
Really?
What would you recommend?
Depends on your third subject. What's your other one?
Descent to.
Nah, I wouldn't recommend it. Because Desmond's a group project. And 2400s might be hard. With term 2, right? Yeah, it'll be a bit harder. And 1300 is alright. Alright, let's get started. Forces on a submerged body. Let me start the recording. It's already going. Beautiful. So, there are 3 cases that we look at when it comes to fluids. A vertical plane, an inclined plane, and a curved plane. So what that just pretty much means that, okay, imagine this. Imagine this is a flat gate, right? A sluice gate. Which just means that you can open, close, whatever. Imagine this is a flat plane and you've got water hitting it like this, right? It's submerged. Right? Bless you. That thing will essentially apply a force onto this gate or this vertical body object, right? We call that force a hydrostatic force, right? So it's force due to a fluid, right? So let me quickly explain. Give me a second. Hey, so what we're looking at right here, we're looking at a side view. Okay, so pretty much what I'm looking at right now. Alright, so this is the gate. There's water coming in from this direction, and it's applying a force. Alright, so the red line that I have the arrows. Is it raining? Oh shit. This is your pressure distribution. Right? As we said earlier, at the top it's going to be 0, and then as it increases, your depth increases, your pressure is going to increase as well. Going this way. This is my gate. If you guys have done ENGG2500, you guys will know that we can make this into one singular force. So 2/3 through, exactly. So the centroid of this shape is somewhere over here, so 2/3 of the way down, 2/3 of h, and this force is given by F. This is my hydrostatic force. The formula for that I've listed over here. Right? So the way you figure it out, area of this shape multiplied by the width of the gate. Yeah, okay, I'm just going to assume everyone's done ENGG2500. It's usually just the volume of the stress block. Okay? So, I've actually drawn it right there. So, this prism is the force of the water acting on the gate. Right? To find the equivalent area of it, or the equivalent force of that volume, to find the equivalent force of all that pressure acting on the gate, you just find the volume of that block. Okay? Yeah, I don't know. There's not really much to explain here. It's just, you can use the formula. That's why I just use the formula. It's just a few different scenarios. So this is the second scenario. This is a more common scenario you'll see. And this is how you see it in an exam as well. So over here, you have your side view. So again, I'm looking at it from the side here. Your second view is going to be looking at it from this angle, looking at the gate itself. And my third thing is going to be the pressure distribution acting on it. Okay? Most of the time this actually isn't given to you, you're going to have to figure it out yourself. But why does the pressure distribution look like that? Why doesn't it? So the gate right now, so this is my gate here, but my water table, and my water level is up here. Why does the pressure distribution not look like this? Does anyone know? Why does it look like this? Why isn't it just a triangle like this? Not quite. Why does it already start with some sort of pressure up here? Why doesn't it not start at 0? Exactly, perfect. It's already at a certain depth down. The top of the gate is over here. So at this point, let's say we have an object here, there's already going to be some sort of pressure, right? So I'll call it H1. Okay? So the pressure here is going to be rho times H1. Oh, sorry, gamma times H1. Similarly, down here, let's say this is H2. This is going to be gamma H2. Does that make sense? Yeah. Good pickup. Good point. And the way we figure it out is by integration, but we don't want to do integration, so you're going to use formulas instead. There's two different formulas you can use. Okay? The first formula is just the volume of that trapezoid. Yeah? So if I draw this out in 3D plane, this is what it will look like. Yeah, I guess. Can you guys kind of envision that? Make sense? That's this thing in 3D plane. So I'm pretty much looking at it, extending that outwards. Right? That formula in the middle is just the volume of that block. Right? So this is a trapezoid. The formula I personally like using is just a general formula. Right? It's just gamma times HC times A. Okay? HC being this thing here, the centroid of the gate. So the only time this formula becomes really hard to use is when you have like some sort of stupid shape like this. You get it like that. Like where the hell is this centroid? You don't know. It might be here, might be here, might be here. You don't know. For a rectangle, really easy. It's gonna be right in the middle. Okay? For a circle, right in the middle. For a triangle, I'm actually not too sure. But that HC value is the centroid of the gate, and A is the area of the gate. Yeah? So that's another way you can find F. Oh, shit. Okay? Another thing you might be asked to actually find is the point of application. So where is that force actually acting? Okay? For that, there's another formula which is also given on your formula sheet. You guys don't need to know the derivation of the formula. Again, just know how to use it. Okay? So you have IXX, which is just your second moment of area of the gate. For a rectangle, it's BD cubed on 12. For a circle, I don't know what it is. It's on the formula sheet. Same thing for a triangle. And then yeah, all you have to do is apply the formula and shit. And you are. I didn't do it because I did it in mechanical stream, but if you did it with Wade Gag, you probably would time it. Yeah. So like, you might have seen the IXX is equal to BD cubed on 12, and then for different shapes as well. Yeah.
They usually just did rectangles.
Yeah. Yeah. So yeah. Any questions? Sorry? All good?
Yep.
Beautiful. Now, and on an inclined surface. Now imagine this thing. Now on an incline. Alright, so pretty much, this is your gate, and you've got water acting on it like this. And that's your gate. It's an inclined plane. However, the formula doesn't actually change. It's exactly the same. The only thing that changes is your HC. Okay? It requires a bit of geometry to understand. HC, as we said earlier, is this height to the centroid of the gate. So if I go up here, it's the height from the water table to the centroid of the gate. Similarly, over here, if my centroid is here, I'm going to take this height as HC. You're not always given HC. You're going to have to figure it out yourself sometimes. So you're going to have to you're going to have to find what YC is. They usually give you the angle as well, so you'll be able to find HC pretty easily. And yeah, you just chuck into the formula and you find your hydrostatic force. The point of application is a bit weird now. So, because it's an inclined plane, your point of application, YP and X, there's going to be two different ones. XP being where it's acting horizontally, YP where it's acting vertically. So YP might be like down here, XP might be like here, and then yeah. Like for this one, you can technically find both as well, but XP doesn't really matter because XP, we know it's going to be acting on the gate. XP doesn't change, right? Like this is XP. There's nowhere else it can act. It has to act on the gate. Right over here, on the gate, it can act here, 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 wherever. Right. The formula is varied just a little bit. You have IXY in this case, right? IXY is your polar moment of inertia, which for rectangles is just 0. For circles, it's just 0. For ovals or ellipses, it's also 0. Triangles, I have no idea. I'm pretty sure the hardest they can ask you is like a circle. They could ask a triangle as well, I'm not sure. But I think last year, I don't know what they asked. I think it was a rectangle.
Last year's exam was cool.
Yeah, I heard it was pretty bad. Oh, it might have been like the zigzag one. Yeah.
I think it was zigzag.
It was zigzag?
Back then,
Yeah, but the zigzag one, the way to interpret it is...
It's like a zigzag here and a zigzag here.
Oh shit, really? That's weird. So like, this is, I guess, how... Like, let's say it was just a zigzag like this. This was your gate, right? And you've got water acting like that. The way to interpret it is, imagine you're looking at it this way. So if this is my gate, it's a zigzag. The water's going this way, I'm looking at it this way. What shape do I see? I'm not going to see the zigzags. The projection is just going to be a rectangle. Yeah. So that's how I'm going to treat it, like a rectangle.
Were you meant to put that in zigzag?
I think so. I don't know. I'm not sure. I think.
Hopefully they go a bit like this.
Yeah. I'm hoping because that was really, really hard. Like I still don't know how to like properly do it. That's just my interpretation of how to do it. And yeah, forces on a curved surface. It's really, really long, so I'm not going to go through it today. I do have a few videos on it though. On YouTube. Hey, give me a sec. Let me get a tissue. And then we'll continue with the Okay, continuity. There's a few things that you're gonna have to know. Something called flux. So there's three different kinds of flux: volume flux, which is the most common one that we use, mass flux, and momentum flux. Momentum flux is its own topic by itself. It's on momentum. But volume flux and mass flux I'll quickly go through. So the way to interpret volume flux, it's the volume of water. I guess, hold on. Let me do a demonstration. So imagine this is like the entrance of a pipe, okay? The flux, the volume flux, is going to be the amount of water flowing through that entrance or that opening per second. As you guys can see from the formula, meters cubed per second. So it's the amount of volume flowing per second. And it's given by area times velocity. Area times velocity. Okay? Similarly for mass, it's going to be mass per second. Right? So you're given the mass times, I guess, mass per second. The formula is density times Q. Q is our flow. Yeah, so flow is given by Q, right? And yeah, so this is an example that I made last year, calculating fluxes. So let's say you have a pipe with diameter 0.5 meters, and you have some sort of water going in, right? The average velocity given is 2 meters per second, right? Find Q, which is our flow or our flux, right? It's going to be given by A times U, A being the cross-sectional area of that opening, right? So pretty much this area here. Okay? So area of an opening, which for a circle is pi r squared or pi d squared on 4. Times that by velocity and you get your answer. Pretty chill, pretty easy. Okay? Alright, any questions about that? That's pretty much all of continuity, really. Alright, the other thing I just want to quickly touch on is control volumes. It's pretty much the volume of... Wait. Oh shit. Oh, fucking hell. Oh, thank you. Fucking hell. It's like the amount of volume that you're going to be analyzing. So for example, for a pipe contraction like that, all we really care about is this volume here. Right? It's pretty hard to actually like visualize, and most of the time they'll just give it to you in an exam. You guys don't need to really worry about it. Okay, Barker hydraulics. Oh, this is actually also part of continuity. Sorry. So we have two equations. So continuity equation, we have two. We have the Mama formula and the Big Mama formula. Nick, do you know about the Big Mama formula? The Big Mama formula. So this formula up here, so I'll highlight it. This formula is, as I've mentioned it over here, is when your dV on dt is equal to 0. Okay? So that just means your change in volume over time is 0. So your volume doesn't change. So if you imagine a bucket, so the reason we call it bucket hydraulics is because it's like a really good way of visualizing of what the hell's going on. So imagine a bucket, okay? So I've got a bucket, and down here I've got a bit of a leak. Okay? So it's already got some sort of volume. That's a volume symbol, by the way, for you don't know. It's a weird, it's like upside down here. Yeah. So you have some sort of water going in. Let's call this Q in, and you have some going out. Let's call this Q out. Okay. So that first formula is when your volume changes 0. So the volume actually in this bucket, the amount of water is 0. That means these two have to be balanced out. So the amount of water flowing in has to be equal to the amount of water flowing out. That makes sense? Another case that we have, which I like to call the Big Mama formula, is when it's not equal to 0. So it's not equal to 0. That means my volume actually fluctuates over time. That means these two are not balanced. Yeah? So my Q in, Qi is not balanced. So the amount of flowing in might be greater than the amount of water flowing out. So if the amount of water flowing in is greater than the amount of flowing water out, how does my volume change? Does it increase or decrease? Sorry? So let's say this amount of water flowing in is more than the amount of water flowing out. It's going to start filling up, so it's going to increase. Similarly, if this was bigger than this,
Start draining.
it's going to start draining. Good. It's going to reduce. So here it is. Draining, filling, volume. Yeah. And if it's equal, as I said earlier, there's no change in volume. So in some questions actually, they don't give you what B actually is. Yeah. Yeah, so that's our volume of the water. I don't know why they did that, but not to me, the area, the minor depends on how big it is, right? So I'm drawing up a quick demonstration of what dV on dt might actually look like. So this is another formula for dV on dt. You have dV on dt. If you guys have done a bit of math before, you guys will know that as your height changes, your area might stay the same. So here's another way to do it. A times d actually it's like change of rates, or I forgot what it's called, where your volume is going to be equal to A times H. A is the exposed area, so A times. Okay. So that's for our volume flux, okay? Q in is equal to Q out. We use this a lot, okay? When you guys do pipe flow, you're going to need it in every single question, alright? But you get used to it, it's not too hard. Right, so now we've got one for mass flux as well. That's literally, it's just one formula. So obviously mass doesn't change, right? Mass, momentum of mass, oh no, what's it called? Conservation of mass. Mass can't change, so there's only really one formula for this. Ooh, what's up? Come on in. Good? TC. Alright. So these are kinds of problems actually considered. So where your area changes, it's down here, but usually your area stays the same. This is in your lecture slides. I'm not going to go through it really. It's not too important really. Okay, so conch, you missed out on just a little bit. You've gone through fluid properties, a bit of hydrostatics, right? There's one thing I didn't go through in hydrostatics. It's called buoyancy. It's really easy. It's like 1 or 2 formulas. Yeah. Continuity, right? That's week 3 content. So I just finished that off. I can go through it with you later, anyways. It's alright. And then energy, which is what I'm about to go through right now. So energy. One second. I need another tissue. Energy itself, like by itself, is a small topic, but you guys use this energy formula to Bernoulli's equation all throughout the course. Pretty much the rest of the course, you guys will be seeing this like every single day. There's three parts to it: pressure head, velocity head, and elevation head. And this is pretty much just talking about pressure. This is talking about velocity. This is talking about elevation, right? Within a pipe, okay? And this is what we call the total head when you combine it together. As you compare it between 2 different pipes, right, that are connected together, your head actually doesn't change. You might get head loss, which is covered in pipe flow, but your head in general doesn't change, right? And it's constant along a streamline. Sorry, not 2 pipes. As long as the streamline is constant, which streamline you guys will get into it later on. Okay. Pressure, velocity, head. What else is there to really talk about for energy? Oh yeah, the units. So, anyone know what the units for head is? Any? Honestly, I had no idea when I figured it out. But if you guys want to take a look at it, so let's take a look here. So we have pressure, which is given by kPa, divided by density, which is kilograms per meter cubed, and gravity, which is given by meters per second squared. Alright. So first thing we notice, oh, by the way, kPa, we can reduce it down further because we know that pressure is force over area. Is that true? Yes, that is. So we can say kilonewtons per meter squared. Okay, so this thing over here is newtons per meter squared. By the way, this is something you guys want to learn later on in the course, deriving units. Alright, so that's where dimensional analysis comes in. You guys are going to be deriving units by yourselves. So the meter here cancels out. You get kilograms per meter squared per second. So the meter cubes cancel out. You get newtons on kilograms per second. Shit. Blah blah blah. It becomes meters. Alright? So the units for head is given by meters. Head is like a way to convert energy into like a distance. Right? The theory behind it you guys don't really need to know. But when you do a bit of pipe analysis, right? As I said earlier, the changes in pressure. When you measure pressure, we're using a piezometer or manometer. It will change, and that change in height we call head. Alright? I think. But yeah. Essentially, you guys will be using this formula when, like, let's say you have a pipe here, and it expands like this. This is one case. If you guys remember, Q is equal to A times V, or VA. Velocity times area. Yeah? I want to ask you guys a question. If my velocity stays constant, let's say 2 meters per second, stays constant, how will my flow change at this point? Let's say this is point A, point 2, point 1, point 2. How will my Q change? Exactly, so my Q2 will be less than my Q1 because the cross-sectional area at this point is larger than the cross-sectional area at this point. Okay. So A is smaller, blah, blah, blah. But usually my Q doesn't change. Usually Q stays the same. What changes is the velocity. So the fact that I said velocity stays constant is wrong. Sorry? Yeah, exactly. Oh wait, the velocity. Oh yeah, sorry, your Q would increase. Sorry. I meant, what I was meant to say is that if Q stays the same, yeah, sorry, you brought up a good point. Your Q would increase then, because my area is increasing. So let's say V stays constant. Yeah, V is velocity. My area here and my area here is increasing. The area is getting bigger, so my Q is going to get bigger. Yeah. Well, the question I had was if Q stays constant, which is mainly the case, how will my velocity change? So if V1, V2. In this case, V is going to decrease. Yeah, I was thinking about velocity there. Sorry.
And you were asking about flow?
Yeah.
More area, so more
Yeah.
volume.
Exactly. Yeah, so I actually had it wrong. But yeah. Yes? Oh, it's Q. So So I just write my Q's a bit weird.
Okay, so Q equals Q.
Yep.
Q stands for
Yep. Q stands for
What week is this?
week 3 / week 4. Flow / volume flux. Okay. But yeah, so my V over here is going to be greater than over here. Yeah, good pickup, Pat. Thank you. But yeah. Hey, the last thing I want to quickly touch on is Reynolds number. So Reynolds number is a constant you guys will be looking at throughout pipe flow, right? Week 5, week 7. Yeah, so it's pretty big. Yeah, it's a big thing. What happened? Nick, are you distracting my class? Sorry. So Reynolds number has a formula. It's got 2 formulas. Rho times U times L divided by my dynamic viscosity. So what is Reynolds number? It's a non-dimensional number. Non-dimensional meaning it has no units. Right? So it's just a constant. Used to predict if flow is going to be turbulent or laminar. So we have 3 different cases. We have if it's turbulent, laminar, or transitional flow. In this course, we don't take a look at transitional flow because I guess there's not enough research done into it yet. Right, so it's still being something that's being researched into. Whereas turbulent and laminar is cool. Right? It's pretty flow state. Nah, I don't think we talk about it, yeah? But yeah, turbulent flow is when your Reynolds number is greater than 4,000. Laminar is when it's less than 2,000. Okay? So there's like a few properties that I've put here. Laminar flow is just when it's calm, I guess, the water. Turbulent is when it becomes like hectic. Yeah. Yeah, transitional. Alright. But we don't look at transitional flow in this course. But yeah, you should note it down anyways. L is pipe diameter, yeah. Viscosity, yeah. Another thing you guys will see is critical Reynolds number in boundary layers, but that's slightly different. You guys don't need to worry about it right now. And yeah, down here I've got like something that might be useful for you guys. Some symbols, parameters, and their units as well. So for example, kinematic viscosity is given by that letter and its units. Yeah, you guys see how volume is like the upside down A? It's a bit weird. Yeah. It's in my drive, so I'll give you guys the link for it in just a second. Yeah, so if you guys want to take a photo of this, or like scan it right now, you guys will have access to it. And the recording for this is going to be uploaded on YouTube. I've also got recordings for my workshops last year. Oh, I only did 3. Shit. Okay, I forgot to record last year, but yeah. So this is my drive from when I was a tutor. I had 2024 term 1. Yeah. Oh no, that's so good. My smiley catch. I'm not that old. You gonna be here in 2 years? No, I'm not. Not this year. I'm not allowed to. I'm not sure. Undergrads aren't allowed to teach anymore. Yeah, which is alright. Doesn't matter. Yeah, so I've got some quiz resources from some practice questions provided by Celine. Past papers. I got mine. This is like my workshop notes here. Yeah.
The quiz part, is that the midterm?
Yeah. So these are like my midterm stuff.
Are you allowed to share that?
Yeah, it's already in my drive. Yeah, you guys can take a look.
So our midterm has to be
Oh no, it changes every year. Yeah.
So what is that formula thing?
What formula?
Like,
Oh, it's in my this thing.
Yeah, that one. Right
So if you go to my crash course notes, it should be the very first thing. Fluids crash course. It'll be at the end of that.
We're ready.
We're pretty much done.
How
I might take a photo of your iPad.
Yeah, for sure. Oh yeah, I'm not fair.
So we got Randall's number. Yeah?
Why?
Nah, it's Randall's or Reynolds?
Oh, Randall's number. Oh, Reynolds number.
Then we got Pascal's and Jared.
Jack and Pascal. Alright, thank you guys for watching. I'll end it there.